Hi, there is a particular beauty in the geometric Galton-Watson branching process. It makes possible to calculate the critical case quite explicitly, which is a very unique feature, and I'm going to show you this one in this video. We call the definition of a geometric Galton-Watson process. So we have pessimistic geometric offspring distribution, and the mean of the offspring distribution is Q over P, which is less than 1, so we are subcritical when P is larger than 1/2. We are critical when P is equal to 1/2, and we are supercritical when P is less than 1/2, so the mean is larger than 1. Now I want to concentrate on the critical situation. So Z of Nj is pessimistic geometric of exactly the critical probability 1/2. And remember that the generating function, so that in particular implies that M is Q over P, which is 1/2 over 1/2 over 1. So we are critical. Okay, we know that there is an extinction with probability 1, but we are going to say a bit more about this case. So the generating function is P over 1 minus QS. P and Q are both 1/2. So the generating function is P over 1 minus QS, or 1/2 over 1 minus 1/2 S. If I multiply up by 2, then it's 1 over 1 minus 2s. Okay. Let's see so this was so far the generating function of the offspring distribution. Also, this is the generating function of the number of individuals at time 1. This P of S, the twofold composition of P, is going to be the generating function of the number of individuals at time 2, and that is going to be 1 over 2 minus S, but instead of S I have to take this function again. Okay, let's multiply both numerator and denominator by 2 minus S, so that gives me 4 minus 2S minus 1, so this is 2 minus S over 3 minus 2S. That's the generating function for the number of individuals at time 2. Let's do P of P of P of S. What's that? What do I need to do? Take this function and plug in, instead of S, the original generating function 1 over 2 minus S. Let's again multiply both numerator and denominator by 2 minus S. I have 4 minus 2s minus 1. I have 6 minus 3s minus 2. So in total I get 3 minus 2s over 4 minus 3s. And that kind of starts to be a bit suspicious. There seems to be some kind of a pattern here. And so I actually have a guess. My guess is that when I do the n-fold composition, then I have n minus 1s over n plus 1 minus n times s, which exactly seems to be the pattern here. For n equals to 1, this would give me 1 over 2 minus s. For n equals to 2, it gives me 2 minus s over 3 minus 2s. For n equals to 3, it gives me 3 minus 2s over 4 minus 3s. So that's my guess. And actually that guess is true. How do we verify something like that? You do this by induction. So assume that this is true. Assume this is true for n. Do it for n plus 1. So let's see the n plus 1 fold composition. What is it going to be? N minus 1 s, not s, n minus n minus 1 of something. Well, what is that something? I'm going to plug in 1 over 2 minus s, which is my generating function, into the n-fold composition, which I assume to be of this form. So I'm going to just plug in one more of these generating functions to the assumed form for the n-fold composition, and let's see if that gives me the same formula for n plus 1. So what is it? Let's multiply with 2 minus s everywhere, so 2n minus ns minus n minus 1 over 2n plus 2 minus ns minus s minus n. What do we get? We have 1n in total, and minus minus is plus 1, and we have a minus ns, and downstairs we have 1n in total, and we have plus 2, and we have minus n plus 1s, and this is the same as the formula before, except I increased n plus 1. So instead of n I have n plus 1 there, instead of n minus 1 I have n, instead of n plus 1 I have n plus 2, instead of n I have n plus 1. So this is the same formula, except n is increased by 1. So the induction step is complete, and of course you can start the induction by any of these previous lines up there. So this is true. Okay, it is very rare, it's very interesting, it's very rare, so the guess is true. This is incredibly rare and incredibly interesting to get anything like this in closed form. This is not usual, this is very exceptional for the pessimistic geometric branching process. It's something really exceptional. Now that allows us to actually find the extinction probability. Let's find the probability that there are no amoeba at time n. Let's find the probability that the process is extinct by time n. What is that? Well, we have the generating function of Zn. Zn has generating function n-fold composition of P. All I need to do is plug in the generating function of Z at 0. Plug in 0 for the generating function of Zn, and that's very easy to do. It's just n over n plus 1. So this is the extinction probability. It's n over n plus 1. The probability of survival by at least time n is of course 1 minus this, which is n plus 1 minus n over n plus 1, or 1 over n plus 1. So the probability that the process has not died out by time n goes like 1 over n plus 1. It's a polynomial decay. This is a polynomial decay. It is going to 0. The process will eventually get extinct. The limit of this probability is the extinction probability. The limit of this probability is 1. The limit of the survival probability is 0. So the process will get extinct with probability 1. But the way to get there, the convergence to get there, is only polynomial. It's only like reciprocal of n, which is quite slow. It's much slower than the exponential bound we found using the Markov inequality for the subcritical process. So critical process, and that is typical for critical processes. For critical processes, usually what we see is a polynomial decay, a very slow, much slower decay than the usual exponential decay in the subcritical case. Okay? So when m is strictly smaller than 1, subcritical case, we proved a an exponentially fast extinction, whereas here in this critical example we see a polynomially fast extinction.